Hi. In this second video, we will take off where we stopped in the last video, which is we performed the residual strength analysis, and we now know that the structure will sustain the damage, and we know that the critical crack length, which we do not ever want the crack to reach, is 128 millimeters. In order to perform the crack growth analysis, I will start with the same high-level configuration file for the panel, but I have to make three important changes in the definition here. The first one is the initial crack length. For the linear strength analysis, I could start with a very long, large crack because it was not important for the final result. But for this case, I actually have to put the initial crack length as the minimum detectable size for a crack. And the minimum detectable size obviously depends on the technology for inspections that will be used for this part of the structure. The second change is that now I just want the regular fatigue loads. I don't want limit loads. So instead of this 260 very high load, I will just change this to 100 megapascals. And the last change I have to do is when we did the residual strength analysis, I considered the center of stiffener to be broken because that's a certification requirement. But in this case, I want the center of stiffener to be intact. And these are the changes I have to do. I'll click OK here. It is asking me, because I changed the configuration file, if I want to save it. I will save. And we have now the panel created for us. We can see that we don't see the crack here anymore. It is there, but it is very small, so I have to zoom in quite a lot to be able to see. We defined it as only 2 millimeters long. And now we can perform another crack growth analysis. But in this case, because the loads are much, much lower, I will leave the elastic attachment behavior. We'll check that after the analysis to see if this holds. Then I want again to perform a crack growth analysis. We know that the crack will start with 2 millimeters, and the final crack length here is the 128 millimeters that we defined to be the critical crack length. And I want to do that using 50 increments of crack growth. Why did I double the number of increments here? Because the crack growth cycles calculation is an integration, and it's very important to have a good resolution in the curve so that I get the most correct number of cycles. And with that, I can just click run analysis again, and it will perform the 50 increments of crack growth. We performed in more increments, but it took only 12 seconds, which is less than the 25 we performed in the residual strength. Why? Because in the residual strength, the attachment behavior was nonlinear. So the XdTd has at each crack increment size perform a nonlinear analysis that has to converge. So that is why, although I'm performing double number of increments, the execution time is less. So first thing here with the results, let's check the hypothesis of the elastic behavior of the attachment, right? So I'll just come here for again in the stress strain chart, and we can see that because the load level is much lower, all attachment positions for the stiffener are behaving linearly, which confirms that using just a linear model is absolutely correct for this case. We can also have a look at other attachment positions. I can come here at results again, attachment, stress, strong, status by location. This will show me, well, the last stage of crack growth, what was the status of each attachment position. And everything is going here as expected. So it's just another way of looking at the problem. And we can now move on and look at the crack growth cycles. I just come here to results again, crack growth cycles. And we can see a typical curve here where the critical crack length of 128 millimeters is reached under around 25,000 cycles. And the final result of this analysis, which would be the determination of the inspection period, comes direct from here, around half this number of cycles, so that we have at least 2 chances in inspections to detect the crack before it reaches its critical length. And with that, I conclude this second video. Thanks for watching.